Okay. So we're looking at our last section before test 2 in here. Okay. So in this section we're talking about polynomial functions and what their graphs look like. A lot of this applies to stuff we've talked about with quadratic functions and linear functions already, because quadratics and linear functions are polynomial functions. And we're looking at these things more generally today. So there's not a whole lot of notes to give. I'm going to give you some notes about how you can know a few things about what the graph of a polynomial function looks like. And then really it's just applying those things. So what we'll do is we'll do some examples. And we'll work through some examples after that. So if we're talking about a polynomial function, we classify these things by what we call the degree of the polynomial, and we'll clarify that in just a minute. Yep, it's n, like, yeah, it's of degree n, lowercase n. And you could call it anything, that's just the variable we're using. So since it's a polynomial function, we'll call it p of x. And then we have a general way we write these down. It looks a little strange if you haven't seen it before, so just hang in there with me, and then I'll talk about what each little piece means. So our first term we'll call an x to the n. And then the next term we would call an minus 1 times x to the n minus 1. And the idea is we're going to count down, so every term we go, we're just subtracting another 1 from the power. So we're going to skip some stuff in the middle and get down to what the other end of this thing would look like. So we would count down from n until we get to a1 x to the first power. And since it's a 1 exponent, we don't have to write it. And then our last term we would call a0, and it does not have an x with it because it would be x to the 0th power. Anything to the 0th power is just 1. Okay. And so you've seen examples of these before, you just may not have seen this the way this is written down. So the idea here is that we have some power of x, okay? And whatever the biggest power of x we have, okay, that's the one we're calling x to the n. So that biggest power, okay, we would call n here, and then we're just saying we're subtracting until we run out of powers. So this term, the one that has the x with the biggest exponent with it, okay, that's called our leading term. Okay. And specifically, whatever our largest exponent is with an x, that was the number we were calling the degree of our polynomial. So the degree of a polynomial is just the largest exponent on an x, on a variable. And I've probably used the phrase leading coefficient before. That's just the whatever numbers in front of our leading term. So here are these an minus 1, all the way down to a1, a0. Those are just numbers, those are just coefficients. Right? Exponent, yeah, you could say the largest exponent on a variable, yeah. So we've kind of used the idea already. Because we've had, with quadratics, these are quadratic functions are polynomial functions. So if we had a quadratic function like this, and that's in that same form. So here we would say our leading term is 2x squared. Because x squared, that's our biggest exponent. So a quadratic function is a degree 2, because that's the biggest exponent we have. And you can kind of see how the pattern works out up here. We've just got coefficients with every term, and then when we write it in this kind of standard way, we have x to the second power, x to the first power, and then x to the 0th power, which is not there. So that's all that's happening here. We're just being real general, like we could have something with x to the 7th power, and then we'd have x to the 7th, x to the 6th, x to the 5th, x to the 4th, x to the 3rd. It's just longer, okay, but it's the same pattern. So we just need some of that to be able to talk about polynomials, okay, mainly that idea of degree and the leading term. Okay, so there are some general things we can say about the graphs of polynomials. Okay, so anything you can write down like this from starting at whatever power you want to. Okay, so we can start at x to the 99th, okay, and count down. This is still going to be true for these. So anything we can write like a polynomial. Let's put a line here. Any polynomial you can think of, we can say this fact about its graph. Let's say the graphs of polynomials are continuous. Okay, and we'll go into some more detail about what that means. That means the graphs are smooth curves. And it means a little more than that. We're smooth curves with no holes, jumps, or sharp corners. And this idea of being continuous is developed a little more when you get into calculus. But for us, our definitions is going to be good enough for us to just say it means it's smooth. We don't have any holes in the graph. We don't have any jumps. We don't have any sharp corners. Or another, if you're not trying to be too technical, another good way of talking about a function being continuous is you could say that you can draw the graph without picking up your pencil. And so you start on one end and then it's all connected and smooth. You can get to the other end. So let's look at some things that would not show up on the graph of a polynomial. Okay, there's tons of ways they can look. Okay? So let's talk about, because of this continuous idea, some things that are not on graphs of polynomials. So let's do this one first. So we got a curve here, but then we've got a break in the graph, and it goes from there. Okay, so that's what I would call a jump. Okay. So if you have something like that, then that's not a polynomial. You don't even have to see the function definition. You just know from the graph if you've got something like that in there, it's not, well, I skipped a lot of that, not a polynomial. Okay. be a jump. Okay. Here's another one. So we can kind of think about graphs that are similar to absolute value. So there we have a corner. That's not allowed, so this one would not be a polynomial. So absolute value function is not in the polynomial family. And then our other one was a whole. So, well, let me change colors. So, well, I'm thinking the best way to draw that. Like that there. If we leave a point out on a graph, you'll see an open circle sometimes on a graph. That means that point's not defined. And so that's what I'm calling a hole on the graph. So this one would not be a polynomial. Okay. There are other types of functions that can have those things, but polynomials cannot. Okay. And so that's one quick thing. Our big goal, okay, is to be able to match up a function with its graph, okay, a polynomial function with its graph, or to just be able to look at a graph and say, yeah, that would be a polynomial, or that would not be a polynomial. So we're not going to get into all the nitty-gritty details on every little aspect of the graph of a certain polynomial. We just want like the big picture. We want the big picture stuff that we can tell from looking at a function. Okay. So one of those big picture things that we need to know, okay, is we want to know, like when we get on the far extremes of the graph, so like if we go really far left on our graph or really far right on our graph, we want to know what the ends of the graph are doing. We call that the end behavior. Okay. So with polynomials, we really only have 4 choices of what can happen to the ends of the graph. Okay. Either both ends of the graph go up, okay, that's like x squared, or both of the ends of the graph can go down, that's like negative x squared, or we could have one end goes down, the other end goes up. And if it goes down on the left, up on the right, that's like x cubed. Or we could reverse it, right? We could go up on the left, your left, and down on your right, okay? And be like negative x cubed. So we only have those 4 situations, no matter what degree our polynomial is. Okay? Its end behavior has to be one of those 4 things, right? So either both up, both down, or they're opposites, and then we can figure out which way that would be. Okay, so let's write down our rules here and for end behavior. And really, if you just remember those 2 graphs I mentioned, you don't have to like memorize a rule. Okay. So the 2 graphs that I keep in mind trying to figure out end behavior, the graph of x squared and the graph of x cubed. Okay. So at the first one, x squared, looks like this, right? It's a parabola that opens upward. And then x cubed, if you recall it starts down at the bottom and then goes up. I say you only have to remember those 2 because for the other 2 cases, you just put a minus sign in front of everything, and then they would both go down. Or if you put a minus sign in front of x cubed, it flips. It's up on the left and down on the right. But we can write out the rules too. Okay? You can remember it either way. And so we've got 2 cases. Okay? So case 1 is if we have an even degree I'll just put this off over by itself. Okay? If we have an even degree polynomial, so that's like we have our degree is, or our leading term is x squared, x to the fourth, x to the sixth, right? Any even number for our biggest exponent. Okay. Then two ways the graph can look, right? Either both ends of the graph go up, and we really don't care about right now what happens in between. Okay. So if that's the case, the way we describe that behavior is we say that our y values go up, or the way we write it is that they approach infinity. Right? So positive infinity is up, negative infinity is down. If we're going left, right, positive infinities to the right, negative infinities to the left. So it says our y values go up as our x values go to the right, and our y values go up as our x values go to the left. Oops, sorry, left, negative infinity. Okay. So this is saying as we go to the right on our x values, our y values are going up. And as we go to the left on our x values, our y values are also going up in this case, right? Both ends go up. And that happens in the situation just like we have with x squared. So that happens if our leading coefficient, is it showing up? Okay, let me do what? Our leading coefficient is positive. Okay. So that's like with x squared, right? Our leading coefficient there would be 1. That's positive. So then we get that parabola where both ends go up. Okay. Second situation, we're still thinking about even degree. Okay, so our degree is still 2 or 4 or 6 or 8, something even. The other thing that can happen is that both ends of our graph go down. And then again, we're not worried about what's happening in the middle right now. And we do know it's some kind of smooth curve with no jumps or holes or breaks or corners. But so the way we would describe that, and when both ends go down, is we would say our y values approach negative infinity, right? They go down as our x values go to the right, so toward positive infinity, and our y values go down as our x values go to the left. Oh, sorry, hang on. No, that's right.
Okay. So when you're saying, okay.
Down, yeah. Negative infinity means down, yeah. Mm-hmm. Yeah. Yeah, it is. It's hard to get used to what that's saying. So, yeah. So, looking at the graph, okay, our y values go down when our x values go to the right and when our x values go to the left. Right. So, on the left side and on the right side, our y values are going down. That's what it's saying. Yeah. Okay. And that happens when our leading coefficient is negative. Okay, so even degrees are not too bad to remember if you go back. So if we have an even degree, one thing you can know is both ends are going to go the same direction if we have an even degree. They either both go up or both go down. And the situation where they both go up is a positive leading coefficient. The situation where they both go down is a negative leading coefficient. So again, if you just remember that graph of x squared like we talked about in the last section. Okay? Positive leading coefficients like a smile, they both go up. Negative leading coefficients like a frown, they both go down. Okay? And the one that's a little bit trickier to remember is if we have an odd degree. So we'll cross that off and we'll look at odd degree polynomials. So linear functions fall into this category because a linear function is degree 1. They're a little weird because they're straight lines, but you can also think about like x to the 3rd or x to the 5th or x to the 7th. Any of those will behave this way. So if we have odd degree, two situations. Either it goes down to the left, up to the right. Something happens in the middle. In that case, the way we would describe it, we would say y goes up toward positive infinity as x goes to the right toward positive infinity. And y goes down toward negative infinity as x goes left toward negative infinity. So the left side of our graph goes down, the right side of our graph goes up. That happens when we have a positive leading coefficient. And so that's the one I say to remember there is x cubed, because our graph of x cubed, it goes down to the left, up to the right, and it has a positive leading coefficient of 1. So then if you can remember that, it's not hard to remember the negative leading coefficient case because it flips them. That minus sign just switches things around. So it's our last case, right? We've only got 4 possibilities. So last case is if it goes up to the left, down to the right.
Odd.
Yeah, these are both odd. Yeah. So the evens, they both go the same direction. The odds, they go opposite directions. And then the trickier part is just remembering which way is which. So here, we'll go ahead and write down this is a negative leading coefficient. And so the way we would describe this behavior is we say our y values go up. Well, let me do the right side first. I think that's how I did the other one. So we'll say our y values go down as our x values go to the right. And our y values go up as our x values go to the left. If you're looking at the negative signs, right, they're flip-flopped. So with that information, that's all the new stuff. Okay? But we're going to look at some examples, okay, figuring out an idea of what the graph's going to look like for some polynomial functions. So we use this in behavior idea along with some stuff we've already talked about, okay, like x-intercepts, y-intercept. Oh, no, I do have one other thing to say. On a polynomial function, well, you can have them on other functions too. We have these curves, right? We'll have shapes like that in there sometimes. And the idea is if we're just looking at just this part of the graph, okay, we can look at any part of the graph we want to, but if we're just looking at a piece that looks like this, okay, then we call any of the dips, right, where we have like a valley, those have a name that we call a local minimum. Okay. So with polynomials, right, it's not the actual smallest value of the function because they either go up or down, right, forever, right, one end to the other. But locally, just around that area, when we have a valley shape like that, we call it a local minimum. And when we have a mountaintop shape, we call that a local maximum. Maximum. And the other thing that I want to tell you about these here is that if we have a polynomial, we're going to just call it of degree n. N is just some number. And we can put a cap on how many of these valleys and how many of these peaks, how many of these local minimums, local maximums it can have. So the maximum number of valleys and peaks together, right, combined, that a polynomial can have, if our polynomial is of degree n, then it has at most n minus 1 of these valleys and peaks, and we call it a local minimum or a local maximum. If we're talking about the combination of the two, where it could be either a minimum or a maximum, has a weird name. We call them local extrema. So a local extrema is just either a local maximum or a local minimum. So what are we saying there? We're saying for several reasons now, we know this cannot be x squared, right? This could not be the graph of x squared because the degree of x squared would be 2. And here we've got 2 local extrema. That's not allowed. The maximum number of local extrema we can have would be 1, 2 minus 1. Right? And that's not that impressive for x squared, but the idea, is we can put an example in here. Okay. So here's a polynomial function. We would say f of x is degree, what would we say the degree is of that polynomial? 7, yeah, it's our biggest exponent. So we say f of x is degree 7. So its graph has at most, what's the most number of peaks and valleys it can have? So it's going to be n minus 1, so 6, yeah. So the most peaks and valleys our graph can have on it has at most, sorry. Let's do 7 minus 1, 6, local extrema. Well, second round. I'll have a question to myself. Let me double check and make sure that that is the terminology that WebAssign uses. It may call them relative extrema, so either relative or local. You can say either one. Let me double check real quick though. Yeah, it does. It calls it local extrema. Okay, so. Okay. So like we could list if we had numbers on our graph, whatever our x value is here. We could say there's a local minimum at this x value. We could say there's a local maximum at this x value. Okay, so the values are minimums. Minima is how you say that. And the peaks, mountain peaks, are maxima. Maximum. One is a maximum. Okay. That's the last new idea. Okay, so now let's thinking back some examples. So most of the problems in WebAssign are going to give us a polynomial function and then say pick the graph that could represent this function. Okay. That's what we're up to. Okay, so us doing our examples, we don't have multiple choice, but we can talk about the important parts that we would need to look for. Okay. So let's look at this one right away. This one's a little bit different. Okay, it's not written in that standard polynomial form. Okay. So that makes picking out the degree just a little bit trickier. Okay. So the idea is if we want to find the degree of a polynomial that is, this one that's in factored form. Okay. If we have a polynomial that's like this, it's not in that standard polynomial form. Okay. And if we're in that situation, what we're going to do is we're going to multiply the, I'm going to call it the largest exponent term in each vector. And so what do I mean by that? Well, so if we're looking at this factor, right, so the factor of x, then it's going to be it has the largest exponent in that factor, right, exponent of 1. So I'm going to take and multiply this term. And then if I look at the second factor, which one has a bigger exponent? That kind of seems silly to ask here, but x squared would be the one that has the bigger exponent because the exponent on the x with the 4 is 0. So then I'm going to take x squared, multiply it together. Remember, what we're trying to do is we're trying to end up with an answer that has the biggest possible exponent because that's going to be the one that gives us the degree. So here, if I take those two, x and x squared, multiply those together, I'll get x to the third. So my degree here is 3. And you know, you could have several factors all multiplied together. So you just take the biggest exponent term from each one, multiply them all together, and that'll tell you what the degree of the polynomial is. Sometimes it's written in that standard form and you can just look and see it. Okay. But if not, that's what we do. So all that's doing is that's saving us from having to multiply the whole thing out. Because if you have a bunch of them, it's going to take a long time to multiply the whole thing out. So instead of having to multiply everything, you can just look at the biggest terms and multiply those together. If they're in order, it'll be the first term, but they may not be in order. Yeah. So the term with the biggest exponent in each one of the factors. Yeah. Yeah. Okay. So we'll have another one where we use this in a second. So this one's degree 3. Okay. And the other thing we did there is we also have the coefficients for each one of these, right? It just turns out on this one, both of our coefficients were 1. So when we multiply them together, the coefficient we get is 1 again. But that tells us that 1 is the leading coefficient of the whole polynomial. Okay? So this polynomial we know is degree 3, and we have a positive leading coefficient. Okay. Degree 3, we have a positive leading coefficient. So what's that tell us about the end behavior? That's going to be one of the best things for us to use if we're looking at multiple choice. We'll have some graphs and the different ends will be going every which way. We got to figure out which one matches up to the polynomial we have. So if we have odd, we know it's odd degree. That means the ends are going to go in opposite directions. So any graph where the ends are going the same directions, we can throw those out. Right? That's not going to be the graph. And then even a little bit more, since we know it's positive leading coefficient, it means it's going to go down on the left and up on the right. So that's what our end should be doing, right? It should be going down on the left and up on the right. Stuff that's going on in the middle right now, we haven't filled in any of those details yet. But okay, so that'll let us throw some of our choices out. Multiple choice. Okay. All right, that's usually not quite enough on these web assignment problems to narrow it down to one answer. Okay. So some other things you can look for on these graphs. So our function, I'm just looking at it again, is x times x squared minus 4. Okay, so some other things that can be helpful are the intercepts, the x and y intercepts. Okay, so last time we talked about how to find x and y intercepts for quadratic functions. It's the same idea here with these polynomial functions. So the y-intercept is the easiest one to find. And the way we find the y-intercept, we'll put it down here. If we want to find the y-intercept, we find f of 0, or in other words, we're going to plug in 0 for x. So if we do that on this one, what will we get? We'll get 0 times 0 squared minus 4. 0 times anything is 0. So our y-intercept on this one is going to be at the point 0, 0. That makes sense. We find f of 0. So we're plugging in 0 for x. We get out 0 for y. So our y-intercept is at the point 0, 0. So as far as our graph is concerned, we know our graph has to go through the origin, through 0, 0. So if we have any graph choices that do not go through 0, 0, then we know they're not correct, right? We can throw those options out. Unfortunately, there's probably, on most of these problems, there's probably more than one that will have the same y-intercept also. So we've got one last bit of information, okay, that will 99% of the time get us narrowed down to one choice. okay, on our graphs. That's finding the x-intercepts. So remember from last time, to find x-intercepts, we take our function, whatever it is, and set it equal to 0, and then solve for x. On a lot of these, it's going to be easy. This one's not bad either because it gives us the function in factored form, so it's already factored. So all we have to do is set each factor equal to 0. Okay? So the factoring is usually the hard part of that. But that part's already done for us here. So our function was x times x squared minus 4. So I'm going to set that equal to 0. And since it's already factored, we can set each factor equal to 0. So here's 1, x equals 0. We actually already knew that one because that's the same place where our y-intercept was. Right? We know 0, 0 is on our graph already. But if we take the other piece, set it equal to 0. This thing you could factor, it's a difference of 2 squares, but you don't have to. We can just take the square root of both sides. Just remember when we take the square root of both sides, we need to put in plus or minus. So now we've got 2 other points that are on our graph. Okay, these are our x-intercepts. So the point 2, 0 and the point negative 2, 0. And this one told us 0, 0 was on there, which we already knew. I'll get a better 2 there. Okay, so now we can make sure our graph's going through these 2 points. Right, so we got positive 2 and negative 2, so that would mean our graph has to go through positive 2 through the x-axis, and it has to go through our graph at negative 2. And we've got a little bit more information. Not always super helpful on this particular web assignment, but we do have this other information that can help. And that's that we know our degree is 3. So what's the most number of local maximums and minimums that we can have? 2. Okay? So if you see anything that's got more than 2 peaks and valleys all together, right, then you know that's not it. Okay, so you can throw that one out. So there's several ways this thing could look, okay, but my guess from our information we have is that it looks something like that. So if we filled in, it would look maybe something like that, right? So we've got 1 local maximum, 1 local minimum. It goes through the right x-intercepts, goes through the right y-intercept, and the end behavior is correct. So 99% of the time, that's going to be enough to pick out the graph. If you're in the 1%, okay, where that's not enough information, if you've got 2 that has all those same characteristics, okay, or maybe you're on one that is not in factored form, so it makes it a lot harder to find the x-intercepts. Another strategy we could use is just plugging in an x value. Right? So we could just take our function and we could say, okay, what's my y value going to be if my x value is 3? So we just plug in 3 for x. Right? So there we would have 3. Here we would have 3 squared, that's 9, minus 4, that would be 5, so 3 times 5. So we can get another point on the graph. That would be the point 3, 15 if you plug all that in. Okay? And you can check to see which graphs go through that point. Okay? So you can always do that. You can always just pick an x value, see what you get for y, and then check to see if that point's on the graph you're considering. Yep. Yeah, scroll back down. Yeah, sure will. that good? Let's, I got two more for us to look at. Okay? That don't take as long after you have a little bit of an idea of what we're trying to accomplish. Okay? Got it? All right, so let's think about another graph. Well, actually, since we're here on the computer, why don't we look at what the real graph looks like? So we got x times x squared minus 4. Let me, if I can get on the Wi-Fi here, we'll check it. Wi-Fi's been a little flaky today, but we'll see. Okay. Yeah, all right. So let's do our graph. X times x squared minus 4. See how close we got to the real graph. Not too bad. And there's our real graph. It goes down on the left, up on the right, like we said. It goes through -2, 0, and 2, like we said. Okay. And this one did have 2 local extrema. Okay. That rule about the local extrema, the minimums and the maximums, it only gives you the maximum number it can have. Okay. It can have fewer than that, okay, but it has at most n minus 1. Okay. They can have fewer. So we could have had something that had no relative extrema on this one, and it would have been allowed. Okay. One wouldn't have, because if we only had one peak or valley, that would mean both ends were going the same direction, and that can't happen with odd degrees. So, all right, so let's do another one. Okay, so new polynomial function. This time let's do one that's not already factored. So some stuff, when it's not factored, some stuff's easier. When it is factored, some stuff's easier. Okay, so it's kind of, some stuff's easier, some stuff's harder, either way. Okay. So on this one, finding the degree and the leading coefficient's a piece of cake. Okay. So here our degree is 4, just our biggest exponent. And our leading coefficient, in this case, is just a 1, so that's positive. Okay. So then that makes this one quick to figure out the end behavior. So the end behavior, if we have an even degree, that means both ends have to go the same direction. And since our leading coefficient is positive, that's a smiley face. Right? That means both ends of our graph are going to go up. Both ends will go up. So far, we've already got the end behavior. We know both ends are going to go up. That's from our degree and from our leading coefficient. The y-intercept is just as easy. Okay, it's easy in either form. Okay. So here to find the y-intercept, we'll plug in 0 for x. We'll plug in 0 for x. The first term will be 0. Second term will be 0. So again, we get 0. Okay. So our y-intercept, I'll write down what we're doing there. So we're going to find f of 0 which gives us 0. So our y-intercept is at 0, 0 again. So that point's on the graph. And let's try to find x-intercepts. That part's a little bit trickier here because it's not factored already for us. So it was, I'm just copying down the function again, was x to the 4th plus 2x to the 3rd. So on these, once our degree gets bigger than 2, we don't have as many methods for trying to solve these things. And so since I'm trying to find x-intercepts, we're going to take x to the 4th plus 2x to the 3rd and set that equal to 0 and solve for x. But since our degree is bigger than 2, so if it's degree 2, quadratic, we spend a whole section talking about different ways to solve, right? We could complete the square or factor or use quadratic formula. Sometimes we could even just take the square root of both sides. When our degree gets bigger than that, we really don't have one method. Okay? We really don't have one method for trying to solve these, and that's factoring. That's factoring. So, and then again, we really don't have a lot of different methods for factoring. So it kind of makes it easy on knowing what to do. The only thing we can really try to do is to see if we have anything in common. And see if we have a greatest common factor we can factor out. And so here we do, we have x to the 3rd in common. So we can factor out x to the 3rd. That leaves us with x plus 2. Then if we set each one of these factors equal to 0, the one on the left, if you can just look at it and see that x has to be 0, that's fine. You can think about taking the cube root of both sides if you want to. That's okay too. But we end up with 0 there. On the other one, we subtract 2 from both sides and have negative 2. So the one on the left doesn't really give us any new information. It just gives us the point 0, 0 again. And then the one on the right gives us the point negative 2, 0. And so that one we can add to our picture. I got. All right. So this 0.
Yes.
Okay. So what I'm doing is I'm solving for x, and so since I set the whole thing equal to 0 to start with, this is the x-intercept, right? Yeah. So on these, on the x-intercepts, the y value is always going to be 0. That means that's where it's crossing the x-axis. Right? Yeah. No, good question. Good question. Okay. Yeah. So this 0 is going in this spot, and then this negative 2 is going there. Yeah. Okay, so now I've got one other point, right? Negative 2, 0. So that's got to be on there. Okay. So that may be enough, right? If we're given multiple choice, that may be enough to pick out the graph that would work. If not, we would just plug in some number for x and see what we get for y, and that'll give us another point on the graph. But from this, most of the time, that's going to be enough information. So our graph's going to look something like that. I got a little floppy there. Something along those lines. My scale's a little weird, probably. I don't think our picture is going to be as good this time. Let's see what the actual graph looks like. If we wanted to, again, we wanted a more accurate picture, we could just pick any x value we wanted, plug it in for x, see what we get for y, and that would give us another point. But let's see what our graph looks like. So this one was x to the fourth plus 2x cubed. Yeah. So, not too far off. And it does have the weird little bump here at 0. You can actually figure that out ahead of time. That's just a little bit deeper than we're going. Okay. Okay. So kind of strange looking, but we could have probably picked that out multiple choice. Okay. Let's do one more. So let's see, last one I have written down for us to try is in factored form. It's x times x minus 2 times x plus 5. So being in factored form, that makes finding x-intercepts easier, but it makes finding the degree harder. So our rule for finding the degree is we take the biggest exponent term out of each one of the factors and multiply them together. So this one I have x, well, let me get a different color. This one I have x, this one I have x, this one I have x. So if I multiply all those together, I get x to the third. So we've got another degree 3. So odd degree. And then again, our leading coefficient is 1, so positive leading coefficient. So odd degree, positive leading coefficient. That tells me the end behavior is going to be down to the left, up to the right. Yep, I sure can. Okay. The next thing I would check, okay, you can do this stuff in any order you want to, but to me, this is the best order to go through because once you get the end behavior, usually you can get rid of like half the choices. Okay? And then y-intercept is so easy to check for. That's the one I go for next because sometimes it can be really helpful. On the two we've done so far, it's been at 0, so that's not that great, but sometimes it can be more helpful than others. So y-intercept would be the next thing I would check for here. The way we get that is we plug in 0 for x. And so on this one, we'll have 0 times 0 minus 2 times 0 plus 5. And since that's all multiplied by 0, again, we get 0. So our graph has the point 0, 0 on it again. Okay. A lot of these in the assignment do. Not all of them, okay, but a lot of them do. That's my y-intercept. I put it on the graph. It's also one of my x-intercepts. And then the last big things, we'll find the x-intercepts. So to do that, I'm going to take my function, which is x times x minus 2 times x plus 5. Set that equal to 0. Solve for x. So this part's a little easier on this one because it's already factored for us. So we just set each factor equal to 0. So here's the one I already knew about, x equals 0. Then we get some new information from the next one, and we get that we have x equals 2 at the point 2, 0. And then for the last one, we get x equals -5. So I have the point -5, 0. Let's add those to our picture. So I've got 2, 0 and -5, 0. Okay. And again, one last thing that's easy to check for, not always helpful, but easy to check for is for degree 3. So the maximum number of local extrema I can have is 2, n minus 1. So if I see any graph that has more than 2 peaks and valleys altogether, then that's not it. So this one, let's see, I'm estimating here. Let's see what we get. I think it's something like, yes. So let's check it. So, and I'll go back to that if you're missing anything there. X times x minus 2 times x plus 5. So, okay. Picture's a little off. I didn't bring it up that high. Right. But right general shape. Okay. And so if we stretch it out a little bit, that'll help. Questions on those? Think you kind of got the idea of the process to go through? Some of them are easier than others, right? It just depends on how hard the multiple choice is on them. Right? If you have some that look really similar, then you have to take a little bit more time. But, okay. All right, that's it. Okay. Tuesday will be review day, and I posted the practice test on WebAssign today. Again, that's not worth any points or anything, so don't stress about that part. It's just a study guide. Okay, and we'll work through one of all of those problems on Tuesday. Okay. Everybody get on the sign-in sheet? I think everybody got on, didn't they? Okay. All right, so this will be recorded. Okay,